Hi, this is Dr. Emenacker. In this particular video, we're going to be looking at how do you design a container that will minimize the cost when you take into consideration the price of the materials needed to build the container. This same process can be used either for boxes, like we're going to take a look at in this case, or cans. Let's take a look at what's going on here. So we got a company, Dumpsky Trash Containers Incorporated, needs a dumpster that'll hold 450 cubic feet of refuse. The cost of the material for the sides is 25 cents per square foot, and the cost of the material for the bottom is 35 cents a square foot. These prices are way smaller than what they would really be, but it keeps the numbers reasonable for the problem. Due to trucking constraints, the length must be 3 times the width. Determine the dimensions that'll minimize the total cost of the container. Notice we're not trying to minimize volume or maximize volume because we have a prescribed set volume. It has to be 450 cubic feet. Okay, so I have a sketch of what the dumpster is going to look like here. It's going to be some kind of a rectangular, kind of like a giant shoebox. And we also have the requirement of 450 cubic feet. That's the volume. The volume of a box like this is length times width times height. And notice here we're given an additional constraint due to trucking needs where the length has to be 3 times the width. So I've jotted that down. This is going to come in handy because it allows us to rewrite the equation. Instead of having 3 variables here, length, width, and height, I can now rewrite this substituting 3W for L, okay, as the volume is going to be 3 times W, that was L, times width times height equals 450. This simplifies to 3W squared times H equals 450. And notice we have reduced this from 3 variables now to 2 variables. We're eventually going to need to do a little bit more, but for right now, that gets us part of the way done. Okay, we want to minimize the cost. When we look at this, we have 4 sides to it. Okay, you have 2 sides and 2 ends. And remember, the cost for the material for each of these 4 panels is 25 cents per square foot. So we're going to do this 25 cents per square foot times the total area of the 4 sides. The bottom, okay, the piece that's getting shaded in there, costs 35 cents per square foot. So we're going to do the area of the bottom times the 35. Breaking this down a little bit further, for the 4 sides, we have 2 ends and then the 2 sides of the container. Each of those is going to be times the 0.25, and we have the 0.35 times the bottom. When we take a look at the ends of the container, notice it's the width times the height for the area. And there are 2 of those. So I'm going to do 2 times width times height times the cost of 25 cents. The 2 sides are going to be the height times the length. So these are the 2 sides. It's going to be the length times the height. And there are 2 of those, and they are 25 cents a square foot. And then the base is going to be the length times the width, which is right there, times the 0.35. Okay, so now we have a cost function, the price of the material for each portion of the final container times the area for each. I'm going to also substitute in that the length is 3 times the width. So what'll wind up happening here is I could put in this 3 times the width here and also put it in there, which allows me to rewrite this equation as 3 times width height here and 3 times width there, substituting 3W for L. When you multiply things together, so for example, I take the 0.5 times the 3, which is going to give me 1.5 WH plus 0.5 WH, so we get 2 WH. And then we take this and clean this up. We have the 3 times the 0.35, and then we have W squared. Okay, at this point we have two variables. This, remember, is no longer an area. This is a cost. Okay, so we're working on developing a cost function. Remember that we had earlier up here at the top, from our volume information, 3W squared H equals 450. I'm going to bring that down here and use this in the blue box. I have the 3W squared height equals 450. I can solve for H. H is going to give me 300 or 150 divided by W squared, or I can write it as 150 W raised to the negative 2 power. Which format am I going to use? Depends on which looks easier to substitute in and clean up algebraically. So what I'm going to do is, in place of H in this top equation, I'm going to put this in because I've got some W's that seem that they'll cancel out. When I substitute in the 150 over W squared, it gives me the 2W times 150 over W squared, and sure enough, a W does cancel. That's going to give me then 300, because I have the 2 times 150 over W, plus this 1.5 W squared. Okay, moving forward with this, I'm going to rewrite this 300 over W as 300 W to the negative 1, because as soon as you get your cost function, you want to optimize that, which means take the derivative and set it equal to 0. 300 over W isn't as easy to compute the derivative of as 300 W to the negative 1. So when I take the derivative of this first term, the negative 1 is going to be times the 300, giving me a negative 300, and it'll be W to the negative 2. I'm going to write that as over W squared, because once I get my derivative, I set it equal to 0 and I have to solve. So I'm just thinking about what's next to decide what format I'm going to use for writing my variables. Then when I take the derivative of this, it's going to be 2 times this 1.05 W squared, which is going to give 2.1 W. Setting these equal to 0, I'm going to move the negative 300 W squared to the right side. I'll multiply both sides by W squared and divide both sides by 2.1. This gives me then W cubed equals 300 over 2.1. When you work this out, this works out to be 5.23 feet. So the width is 5.23 feet. Before we go any further, let's verify that this truly is a minimum. There are two ways to verify it's a minimum. One of the things that I could do would be the first derivative test with the 5.23 here. And I could evaluate the first derivative at something like 1. That's to the left of 5.23. And the first derivative at something like 6 to the right. But, that looks like kind of a pain. I'm going to use the second derivative test, which means I'm going to come to the top, take the derivative of this. The second derivative is going to wind up being, well, gosh, how'd you do that? Remember the first derivative, okay, I took this and I rewrote it like this, choosing to write my variable with the negative. When I take the derivative here, it's going to be the negative 2 times the negative 300, which is going to give me 600. W to the negative 3 is over W cubed. 2.1 W is a derivative of 2.1. Now, all I need to do here is to plug in the 5.23. I'm not going to really plug that in. What I'm going to do is I'm going to look at, I have 600, which is a positive number, divided by 5 and some change cubed, that's a positive number. So this first fraction's positive, plus 2.1 is positive, which gives me that my second derivative is positive. And when the second derivative is positive, that means it's concave up. And if it's concave up, you have a minimum. Okay, so I verified that my answer that I'm working with, the width of 5.23 feet, is a minimum. So what I'm going to do next is I'm going to chase down the dimensions. I know the width is 5.23 feet. We were told that due to trucking constraints, the length has to be 3 times the width. So to get the width, I'm just going to take 3 times 5.23, which is going to give me a length of 15.69 feet, basically 15.7 feet. We're not going to get too upset about something like a dumpster over 15 feet long. Okay, so I have my width, 5.23, my length, 15.69. And recall, we know that the volume is length times width times height, and that has to be 450. I can substitute the 5.23 in for the width. I can substitute the 15 and some change here for the length, which is going to then leave us with just the height. I can take and solve for height by dividing the 450 by the width times the length, which is what we have right there. When we work that out, we get a height of 5.5 feet. Okay, so now we know the dimensions of our container, basically 5.23 feet by 5.48 feet tall by 15.69 feet long. To get the cost of the container, I go back to my original cost equation. Okay, and my original cost equation is this, but it's all in terms of W. And if you look at the very top, the value of W is this 5.23, so I'm going to substitute that in there and substitute it in here. And when I plug that in both of those places, it gives a final cost of $86.08. Okay, so these dimensions will give us the volume we need and a minimum cost for the construction of the container. If this was a can problem, we would work it essentially the same. Coming way back up here at the top, for the can, we would take the area of the base times whatever its cost is, plus the area of the top times what its cost is, plus the area of the side times whatever its cost is. And you would have those 3 factors, or terms actually, that you would need to add together to get your minimum cost. You would take the derivative, okay, and you would be on your way. Hope this was helpful, and I hope you're doing well.